lectures. Today and Monday, we'll finish up alkene additions. I don't think we have class next Wednesday, is that correct? So that the following week you have the last two lectures, and then those will be on alkynes. So how do we make alkynes, and how do you do additions today? So today we're going to look at a couple more addition reactions. Broadly characterized, these are 1,2 difunctionalizations of alkenes. So again, we had the issue of what type of electrophile, are they getting the same atoms, or if the electrophile is non-symmetric, or they get different atoms. So we'll look at the regiochemistry today with halohydrogen formation, oxidation, hydroboration, and maybe another one I'm forgetting or remembering. So that's three or four more reactions. And then on Monday it's another 3 or 4, so it's quite a bit per lecture. Any questions before we get started here? So we saw last time we can add halogen using molecular halogens such as chlorine, Cl2, or bromine, Br2. And then each atom of the alkene gets the same halogen X group. That was in a solvent that's non-participating. So an analogous one is now where you're still using a molecular halogen X2, but now we're in a solvent that participates. Participates. That looks weird to me, but whatever. So the take-home message of this, even though I'm showing it as water, any alcohol solvent will do this. So protic solvent, again, they're typically alcohols. So in the one shown here, we're going to use chlorine in water. And so this should say alkene going to a 1,2 halo alcohol, and that's called a halohydrin. So hydrin is another word for alcohol. And we were using this model alkene that was tri-substituted. So that necessitates we consider the regiochemistry. So where it says E equals Cl2, that's your electrophile. That reacts with the pi bond, and then the solvent is going to be the nucleophile that attacks the other carbon of the alkene. So as we see, we form a major product versus a minor product. And essentially under these conditions, we can classify it a couple different ways. The major product is the more substituted alcohol. And then the minor product is the least substituted alcohol. And the reason for that is the mechanism proceeds through that halonium ion. And again, that was the 3-centered intermediate. That has the positive charge on the halogen. So the electrophile interfaces with the alkene, you form that intermediate, and now the X anion is not there in a great concentration because there's more nucleophilic solvent around, and that's what ends up trapping the halonium ion. So we'll write that off on the next slide. to show why there's a difference with these solvents. So one thing I'll point out, this is going to give you an anti-addition, so that's how I've started things off here. And now what I'm going to do is just put in the existing stereochemistry that was present in the alkene. So that methyl group is towards you, hydrogen's away. Ethyl group towards you, and methyl group away there. So that the mechanism is asynchronous. The chlorine will add first, then the OH, and it will do it in an anti-fashion. So that chlorine, again, will approach sort of perpendicular to the pi bond. We'll have a lone pair come down to attack. The pi bond goes up, and then we cleave the chlorine-chlorine bond. So we'll start off by drawing the three atoms involved in that. So Cl, the two carbons, that gets the plus. We'll stick the stereochemistry back in. And so now this is where the solvent matters, because chloride is still nucleophilic, but there's more of the solvent around. It's typically in a large molar excess. So because the halonium ion that halogen is blocking like the top face, the nucleophile has to approach from the other face. But we have a choice. Of which carbon it's going to attack. And since the chlorine is plus, we want to think of this in terms of opening that ring. Which carbon atom would then be the most stable carbocation? So if we look at each of them, so if, say that the arrow to B, that carbon, if the plus charge resided there, it would be 1, 2. It would be a secondary carbocation. If the plus charge resided on that one where it's going to A, that would be 1, 2, 3. So that would be a tertiary. So really we want to evaluate the attack based on carbocation stability. So the solvent is going to attack the more substituted carbon, which is going to give you the more substituted alcohol. So choice A is preferred. So that attacks, that's the bond that then opens up. We just put the stereochemistry back in as we started with. And then we do a proton transfer with water to get us to the major product. For choice B, which is less preferred, it's going to attack the least substituted carbon. And again, we're evaluating that based on carbocation stability. We then just do the proton transfer again with water. And that would give the secondary alcohol as the minor product. Yeah.
Just to confirm, it behaves as if it's forming a more stable carbocation, but it doesn't actually have a carbocation intermediate.
So I guess that could be a point of debate. I think in evaluating it, you could draw it as the carbocation. So that would be that structure. So now a potential issue with sort of thinking of the mechanism of like just being that as like another intermediate. Now you have a sigma bond that could rotate, and you would end up with what would appear to be a syn addition, but it's really not. So I like to think of it is sort of opening from the halonium so that you can still get the trans or the anti-addition. If you think of it this way, there is a possibility that can rotate, and then again your ethyl group would then be behind and your methyl group would be in front.
It's more like a transition state.
Sure, yeah. So the other thing I want to point out is the way that I've drawn this, I showed the chlorine attack from the top face, but it will equally attack from the bottom face. And so you'll get this plus the enantiomer of that. So those would form in a 1-to-1 ratio. Any questions on that one? So what two instrumental techniques would best inform you that you have both the OH and the chlorine? So OH is
pretty unique in IR. And then chlorine is mass spec. So we have 35 Cl to 37 Cl in a 3-to-1 ratio. So that would be D. So here we have a cyclic alkene, so cyclohexene. We're treating with bromine and water. And just under diagnosing those conditions, can you eliminate two choices to start with? So I think I heard C. Which other one? So C and D. And again, the reason you can eliminate those is because you've added two bromines. The solvent in this case has to be incorporated into the product. So that leaves A and B. And the difference between them is, notice the relationship between the electrophile and nucleophile you added. So here they're cis, here they're trans, or another way of thinking of that is syn versus anti. And we know that the mechanism states that those must be anti to one another, so B is going to be the correct answer. Any questions before we move on to the next reaction? Yep.
Is there a scenario where it might be a same product?
I can't think of one offhand. It would probably have to be a pretty unique substrate to give you a syn addition. So the next reaction is called epoxidation. So the simplest epoxide as a functional group is shown there. So it's basically two carbons and an oxygen in a three-membered ring, and that's called an epoxide. And then the variability you can have is just based off each carbon atom. So epoxides react with alkenes such that each carbon atom of the alkene is going to be sigma bonded to the same oxygen. So notice now the two carbon atoms are not getting different things or separate atoms. They're sharing the same oxygen. And the reagent that will do that is a peroxy acid. So you're probably most familiar with hydrogen peroxide. So you probably have some in your bathroom. It's like a 3% solution in water. So if you get a scrape, you pour it on there, it bubbles, or you can gargle with it, get some fizziness. The thing about peroxides is that central oxygen-oxygen bond is pretty weak. And then also the H, that's not your typical alcohol pKa, it's a little bit more acidic, so it has a pKa of about 10. So hydrogen peroxide is, let's say, inorganic. And so there are organic peroxides, and the one that's most common is shown here. It's called metachloroperoxybenzoic acid, or MCPBA. And you see the OO linkage in there. That's the peroxide linkage. And I've highlighted one of the oxygens in blue. That's the oxygen that actually ends up in the epoxide. So MCPBA in chloroform is going to epoxidize the alkene through a syn addition. So because each of those carbon atoms is going to be bonded to that oxygen, it has to be deposited in a synchronous syn fashion. And the fallout of that is, we used that word before, stereospecific. What that is telling us is that whether you're starting with like cis or trans in the alkene geometry, that relationship is held through in the epoxide because there's no bond rotations that can happen that are going to flip them back and forth. So we'll go through this over the next couple slides, and then we'll write the mechanism for it, I think, on the last of these slides. So if our model alkene is treated with MCPBA, we form an epoxide. The epoxide functional group is a 3-membered ring ether. So that's what our epoxide is going to look like. And of the 2 carbon atoms, we see they come from the alkene carbon atoms. All we're then doing is just drawing in the substituents with the cis or trans geometry that you started with. So we're the alkene, it does have cis geometry to it, but overall it's achiral. The MCPBA is achiral. So the stuff we produce must overall be achiral. With that said, if you imagine the pi bond of the alkene, the MCPBA can attack from the top face or the bottom face. So overall, you're going to end up with 2 stereoisomers that will be enantiomers. So this question is asking you the 2 products on top A or the 2 products on the bottom B. What are the correct, what's the correct pair of enantiomers? So all of them have the epoxide. Really what you're evaluating are, see the nature of these substituents, the wedges and the dashes. Which one, A or B, has retained that stereochemistry. So it looks like B. And so that's what we mean by stereospecific. So see, for example, that methyl and ethyl group are on the same side. If you were not aware of what that starting material was, and because the oxygen adds in a syn-synchronous fashion, the alkene that you started with must have those on the same side, and then that methyl group going back. So that's the logic in which a stereospecific reaction occurs. So that said, then choice A would have to start from this alkene. So MCPBA, that's pretty much the most common one for doing this. You're going to end up with that pair of enantiomers, so a racemic mixture. And then overall, the specific rotation of that would be 0. So even though you're starting with achiral things, you're producing molecules with stereogenic centers. But since it's racemic, there's no optical activity. So those are enantiomers. The one on the product on the left is the one I'll draw where the epoxide is forming from the top face. The one on the right, it looks like it's forming from the top face, but again, keep in mind it's an enantiomer. So I've drawn the mirror image of the left one. So I'll give myself some space here. So use some color because I can, because that's the oxygen that's being transferred. And for the most part, the mechanism sort of depicts exactly what is happening, but there might be some trajectories that are not accurately depicted here, but the arrow pushing is what it should be. I'm going to start off from the pi bond. So the pi bond is going to grab that hydrogen. So we're going to form an OH bond. And then we need to break the OH bond. So we'll have that come down. So that will form an oxygen-carbon bond. Then we're going to break the carbon-carbon pi bond and have that attack the oxygen. And so then we have to break the peroxide bond. And in doing so, we'll reform a carbonyl pi bond. So sometimes when you're using more than 3 arrows at once, people will call that a conspiracy, but we'll go with it for our purposes here. And so that deposits the oxygen, and then you get this byproduct, which is a benzoic acid. So that can happen from the other face as well. That's how you get the other product, the enantiomer. And the reactions are pretty easy to run at room temperature. When it's done, you cool it to 0 degrees. That byproduct usually precipitates out, so you can just filter it, and then you're left with your product in the filtrate. So they're pretty easy reactions to run. When you monitor them by thin layer chromatography, they're typically spot to spot. There's really not a lot of impurities to deal with. So over the next couple slides, we'll talk about the advantages to forming epoxides, why this is useful. So we know that these carbon atoms are sp3 hybridized, and so they should have a bond angle of 109.5. But in a 3-membered ring, that bond angle is significantly compressed. So if we just think of it as like an equilateral triangle, the internal angles are now 60. And so there's a significant amount of strain in the ring. And so that makes the epoxide a reactive functional group that wants to open up. So you want to break one of those carbon-oxygen bonds. And this can happen under acidic or basic conditions. And so that will relate back to how we evaluate SN2 and SN1. So in acidic medium, generally speaking, we're dealing with plus charges, so things like oxonium and carbocations. And so we would use the SN1 trend. So with an epoxide, that oxygen has 2 lone pairs. If we were treating it with an acid, I'm just going to say H+, the oxygen will get protonated. So acid, and so this is then a base. And now one of those carbon-oxygen bonds will open up. And so we have to evaluate each carbon according to what class of alcohol it would be. So with Roman numerals 1 and 2, even though we're showing an ether, how would you classify those carbons if they were alcohol functional groups? C. So this would be tertiary, and that would be secondary. So say if we popped open A, that's going to generate a tertiary carbocation. Or if you did B, that's now a secondary carbocation. So under acidic mechanisms, if we're following SN1 trend, we want to form the more stable carbocation, so we would go with path A. So the ionization would occur from Roman numeral 1 after protonation has happened. That generates the tertiary carbocation. So if we're running the reaction with acidic water, now water is going to be a participating nucleophile, so it should be incorporated into the product as highlighted by the red oxygen. Keep in mind as it's drawn, tracking the blue oxygen to start with, what should our product be based on water attacking the more substituted carbon? So the product should be A. And so if we look, we have the blue oxygen, still on top, carbon, carbon, and then the red oxygen on bottom. So overall, even though you're evaluating the carbocation stability, it's like before where the nucleophile is still attacking anti to the existing bond that's going to break open. So that would be our anti-addition. So that's called a 1,2-diol. or another old-timey term is glycol. If you have a car, the coolant in the engine is typically ethylene glycol. And if you've seen, what color is ethylene glycol? Yeah, it can be like sort of a fluorescent or neon orange or green. Does anyone have cats? So if your engine is leaking ethylene glycol, the cats will lick it up because it's sweet tasting, and then your cat will die soon after because it's basically a liver toxin. So watch for any drips in your driveway. So the ethylene glycol is used as a coolant because it can get to lower temperatures than just straight water can in an engine. So under acidic conditions, we're going to end up with the diol as shown, and that has the anti-1,2 relationship. I think I used this word before. For 1,2, that's also called vicinal, or abbreviated VIC, Vic. So if we're operating under the opposite conditions that are basic, we're now looking at the SN2 trend. So we said that this was tertiary, that was secondary. The SN2 trend is methyl greater than primary, greater than secondary, and much greater than tertiary. So when we have a strong nucleophile, it's going to attack the less substituted carbon of the epoxide. And so that would be the secondary one. And the bond I'll highlight in blue here that's the bond that breaks, so the leaving group. But what's weird about it, it's not leaving the molecule. It's still retained by being bonded to that other carbon. It's just the bond that's broken. So your nucleophile has to approach from 180 degrees, so the opposite face. You then break that CO bond, and then the other carbon ends up being an alcohol. So with sodium cyanide, that would attack here. That would break open. And then we want to draw our anti-addition. And then just plug the other substituents back in with their existing stereochemistry. So again, that's an SN2 reaction. Any questions? Yeah. So the question was, can it have major and minor? In that case, probably not, because that other carbon is tertiary, and since it's so hindered, the nucleophile probably can't approach it effectively. So our last slides here in the remaining 14 minutes or so. deal with a reaction that uses boron in the reagent. And so these are called boranes. And on the slide here is Herbert C. Brown, who was a professor at Purdue University and won the Nobel Prize in Chemistry in 1979, along with George Wittig. So I'm only showing Brown on the slide. If you go on to 256, we'll learn about phosphorus chemistry. That's what Wittig was recognized for that same year. They were recognized for their development of the use of boron and phosphorus-containing compounds, respectively, into important reagents in organic synthesis. So Brown had been investigating boron back in the 30s and 40s. And during that time, there was the Manhattan Project to develop the first nuclear weapons. And the reagent he was working on, this borane, was used in these nuclear enrichment processes. So it took a couple years for that to get declassified, and then when it was, he started publishing on the use of them in organic synthesis. The most simple one here is just BH3. That's borane. And what should stand out to you is the boron is tri-coordinate. So it only has 3 bonds. So 3 times 2 is 6. We're used to the octet rule. So there's a lack of a pair of electrons. So essentially the boron is sp2 hybridized, and there's an empty p orbital. And so that makes this a Lewis acid. So a Lewis acid is an electron pair acceptor, and a pi bond is a Lewis base, which is an electron pair donor. So the pi bond is the nucleophile, the borane is the electrophile. And as we'll see, which will become more apparent through the next couple slides, moving from borane, which is BH3, to these other 2 where there's only one BH bond, and you've substituted some hydrogens for carbons. Notice the number of carbons here in these. That makes those groups really bulky. And if we're talking about regiochemistry of now what carbon of the alkene is going to get an H versus the boron, the bulkier the reagent, the more you can control that process. So the reaction is called hydroboration oxidation, HBO, which I think now is Max, right? Anyone got the app? Anyone watch Penguin? Man, that was a great show. Like, if you don't have it, pirate it, watch it. So Penguin it's in the Batman universe. It was superb. So we're going to look at the addition of H and B to the alkene, but ultimately what we're going to produce are alcohols. And so now there's not only the addition of the H and the B, but how do we get the boron to become an oxygen? So there's a unique, kind of neat thing that happens in this mechanism that will be new to us here. So the issue with the borane is now that the boron is the electrophilic atom. The reagent is typically sold as BH3 and then this dot. You might recall that from Gen Chem, that the dot means a dative bond. And so THF is a solvent. And so what it looks like is BH, H, H. You have that empty p orbital. That reagent's pretty reactive. And so the THF just forms a complex with it. So this is THF. It has these lone pairs. And the way that a dative bond is represented is just by an arrow. That's showing that lone pair occupies that to stabilize the reagent. So there's 2 steps overall to the reaction that have different mechanisms involved. But overall, the product is a lesser substituted alcohol. Keep in mind what we learned with the hydration of alcohols. You always get more substituted. So this is a complementary method. So the major product here is a secondary. The minor product is tertiary. So I highlighted in blue the H. The H comes from that reagent, but where does the oxygen come from? So as I highlighted in H2O2, the peroxide, the oxygen you see in the product is coming from peroxide. It gets there because that is initially where the boron was deposited. So you add H and B, and then in the second step of the mechanism, the boron gets substituted for the oxygen. And so we'll talk about how that happens. It's a pretty unique mechanism. But overall, the big thing is, your book will say this is the anti-Markovnikov. So your book will say it's the anti-Markovnikov product, but if you're solely considering boron as being more electrophilic, it still obeys Markovnikov's rule. So the reason you get the less substituted alcohol is how the borane reagent approaches the alkene. And so this is, those other reagents I showed you where you had carbon substituents. So like imagine these were carbon. You want to deposit or approach the H and the B approach the alkene such that the smaller H group interacts with the larger groups of the alkene. So small and large, large and small. So they have to be matched that way. So if we push the arrows, we can imagine, the pi bond coming up into the p orbital, and then we break that HB bond. And so that happens in a syn fashion. So syn and synchronous. And now the second part of it is you have to swap out the boron for the oxygen to get the alcohol. with borane specifically, see how you end up with BH2? Those two other hydrogens are still pretty reactive. And so they'll react with two more equivalents of the alkene, so that overall all of the H's are now added to alkenes. So that's what the R2 means. In terms of a molar amount, we would say 3 moles of this for 1 mole of that. Gives you the intermediate called a trialkyl borane. So at this point, we're not done. We still have to get the oxygen in there. And so because hydrogen peroxide, as I said, that pKa is about 10, you can treat it with sodium hydroxide to form sodium hydroperoxide plus water. And now you have a nucleophilic oxygen that will attack that boron. Because now boron is still now it's electron deficient, it will react with a nucleophile. But if the oxygen's attacking boron, it's still not bonded to the carbon, so something additionally is happening. But overall, you'll do that the same amount of times to end up with your alcohol product. So what is actually happening? The nucleophilic oxygen attacks the boron. So you have this BO bond. The carbon bonded to the boron, those electrons will then migrate to the oxygen. And that will break the weak bond here. So you end up with sodium hydroxide. And now that carbon is bonded to that oxygen. So you formed that CO bond, and then you still have the existing oxygen B bond. So you can imagine, so sodium hydroxide, just displacing that, and then doing a proton transfer to get your alcohol. So just 2 questions real quick we might go over, but I think these are good practice. So if we take 1 butene and do hydroboration oxidation, what alcohol will be produced? So a primary alcohol. So we have to get 1 butanol. So that's, again, going to be your major product. And that would be your minor product. So again, hydroboration is going to produce the lesser substituted alcohol as the major. We're a bit out of time, but the next question is if you have those 2 possibilities, how do you differentiate them according to the uniqueness? So I'll let you guys figure that one out. You have your quiz that's open now. Don't forget to do that. Monday we'll finish up the alkene additions. The following week we'll do alkynes.